Okay, everybody, welcome to ES403 heat transfer. So the problem we have today is a steel slab in a flow of some amount of air at a certain temperature, T infinity. The air has a convective coefficient of 250, and then the steel, with all its properties, are listed right here. You can go ahead and pause the video so you can get all these details. So we need to figure out the time it takes for the interior of the slab to reach 550 degrees C in the slab. Now, the thing when you're reading this problem is to look at in the slab. So in the slab, it could be anywhere here, but when it says inside a problem, it doesn't specify exactly where. You should just assume right at the center of it. So right at the point where it's farthest from anything, that's in the slab, at the center of it. So going ahead and solving this problem here, if you need to, go and take a screenshot of that earlier part so that you know what I'm talking about. But when you're dealing with something absorbing energy from the ambient air, what you usually want to do is find out if you can use LCM, the Lumped Capacitance method. But the only way you can use this method is if the bio number is less than 0.1, or sometimes your professor may have introduced it as much less than 1. Either one of those conditions really work, but this one's just a lot more exact than this one, but it's kind of subjective. Okay, so if we solve for the bio number, Vi is equal to H over Lk, where K is for the solid, not for a gas or a liquid or anything else, in case that slab was encased in liquid. Alrighty, so if you go ahead and solve this out, you'll have 250 watts per meter squared K times 0.05 meters. All of this is from the chart from a little earlier, by the way, in case you're lost. 48 watts per meter Kelvin. And that is going to be equal to 0.26. Okay, which is not less than 0.1. So LCM can't be used. We have to think of some other method than LCM. So that's kind of a bummer, but you should have been given the alternate method by now, which involves theta star. And theta star is equal to theta over theta I, which is equal to T naught minus T infinity all over Ti minus T infinity. Okay, so we're going to solve this out here just to get us a value, because this is actually going to be equal to C1 exponential negative zeta squared times the Fourier number. And hopefully these have all been introduced to you, this whole equation. This is the alternate method to the Lumped Capacitance method. And we can get C1 zeta and the Fourier number from tables, charts, and the values that we're given. So if we can just get this set down, we can find out Ti at a specific time. Okay, so solving this out, we have this equal to 550 minus 800, all over 550, sorry, over 200 minus 800. All of this is in degrees C. That's going to be equal to 0.417. Okay, cool. So we have that. We have Ti. We have this set up now. Now, if you go ahead and look at the table in your book, my book is in table 5.1 in the textbook that this problem came from. But whatever it is, you use the bio number to figure out C1 and zeta. So from that table, zeta is about equal to 0.488. And I say about because you have to interpolate when you look at the table. And then C1 is about equal to 1.0396. Okay. And then the Fourier number is equal to alpha T over L squared. And we need to find alpha now. So alpha is equal to K over rho C. And if you solve that out using the values that we had for the steel plate at the beginning, excuse me, you'll end up with 1.115 times 10 to the negative fifth meters squared per second. So that's alpha. So then, I'm going to take all these values and I'm going to sub them into this equation up here. So I've got 0.417 is equal to C1, which is 1.0396. C1 and zeta are both constants, by the way. They don't have any units associated with them. Exponential of negative 0.488 squared times alpha t over L squared. I'm going to change that parenthesis there. So I just took this part of this equation, brought it down here, brought this down here, and brought it down here. Now you see there's the t that we're looking for. Because we're looking for the heating time to get to a specific temperature. The specific temperature is 550 right here. So we went ahead and solved it, and using Fourier number, we were able to get this located to t because we have L and we have alpha. We have all the other values. So I guess if you want to go back here, you can go ahead and set up this equation and just reduce the Fourier number to alpha t over L squared. I kind of skipped that step, but you can see it here now. We were looking for time, and now we have this whole equation in relation to time. So if you go ahead and start solving that out, you'll end up with t is equal to 0.914 L squared all over, now I'm going to use zeta here for just a second as a placeholder, times alpha, which is equal to 0.841 times 0.05 meters. Excuse me, sorry. Sorry, that's not 0.81, that's 0.9. Yeah, just a second. Double check my notes here and make sure I'm telling you the right stuff. Zeta, and then alpha is equal to L squared. Okay, so yeah, there's a mess up in my notes. 9.14 times this 0.05 meters squared all over zeta squared. Oh, sorry. You might want to double check these. Make sure you do this math on your own. Make sure I haven't made a mistake here. I'm pretty sure I've got it here. 0.488 squared times 1.15 times 10 to the negative fifth meters squared per second. And if you solve that out, you'll have t is equal to 861 seconds. And that's your time to heat the interior of that plate. So what you do is you set up this equation, which is the alternate, the lumped capacitance method. You change the Fourier number into its component equation so that you have it with respect to t. And then you go ahead and start breaking it down, start plugging in values. You plug in chug, and you should end up with t equal to 861. So it's a pretty quick algebraic